Hello, my name is Andy Rivenes. I'm a product manager for database and memory, and I wanted to talk about the new feature in-memory vector joins. So in-memory vector joins is part of in-memory deep vectorization. This is a new framework that we've introduced in Oracle Database 21c for database and memory. And the idea is to take advantage of SIMD vector processing for complex SQL operators that we've pushed down or taken advantage of in the column store. As we run SQL statements, we want to try to use SIMD vector processing, single instruction, multiple data, to enhance that. We're already using SIMD vector processing in our scanning, essentially where SIMD allows us to make comparisons with multiple values rather than just a single value. And so this allows us to take advantage, at least initially, something we're calling in-memory vector joins. So that's going to allow us to further enhance complex joins that we're doing in the column store. So as a lead into that, what I'd like to do is review how a hash join works, and we'll talk a little bit about how we've optimized hash joins with database and memory, and then that will lead us into how the in-memory vector joins feature further enhances the ability to speed up hash joins with database and memory. So characteristics of a hash join: we're joining two tables, usually a small table and a larger table. We're doing it on one or more keys, equality or equijoins, and we build we scan the smaller table. Usually it's the smaller table, but we scan one table, we build a hash table in the PGA, and then we scan the larger table and probe that hash table to find matches that are join criteria, matches on the join criteria, and then return the columns back to the calling SQL operation. So I've got a diagram that try to help explain that a little bit, but as I said, basically we scan. In our case, we're gonna have the stores table and the sales table. So we'll scan the stores table, apply any filter predicates. We'll build a hash table in memory in the PGA. And this is next part is key to what we optimize with database and memory. We then scan the probe table, in this case the sales table, apply any filter predicates, and then we check for each of the, for the hash key, or sorry, for the join key, we actually check the hash table to see if we have a match. If we have a match, that means then we can return that row along with any columns that are part of the query back to the calling SQL operation. You see this in an execution plan with a hash join, and here ID number, starting at ID number 2, and then our build table is the date dimension table, which is the first table that will show, and then our probe table will be the line order table. And if you're familiar with our other examples, and you can see the number of rows involved here, that the date dimension table is much smaller than our line order table, and so that's why it chose date dimension to be the build table. So how do we change that, or how do we optimize hash joins with database and memory? So it's the same basic process, but notice now as we build or scan the stores table and build the hash table in memory, we're also going to create a Bloom filter. So a dense memory structure that allows us to identify membership, or whether or not the rows in the stores table met the filter criteria that we applied. So it does require a filter predicate, at least one filter predicate on the stores table to be able to create the Bloom filter. So we actually then create the Bloom filter and then the hash table in the PGA, and we use the Bloom filter to actually do the join, or instead of having to probe the hash table, we use the Bloom filter to test whether we've got a match in the join keys. So as we scan the sales table in step 4, We'll apply any filter predicates, and we'll also apply the Bloom filter as an additional filter predicate, again, to see if we match on the join key. So that's the optimization that we've enabled within database and memory, along, of course, with the fact that it's columnar format, where we can scan with SIMD vector processing. We can push down our filter predicates and actually test filter predicate matches, or test the filter predicate itself during the scan of the sales table or the table involved. And then so that we only then have to return rows that have matched, and then we'll double check in the hash table to make sure that the join keys do match. Bloom filters have the possibility of having false positives, so that we double check that we've got a valid row from the scan of the sales table. In checking the hash table, we'll also pick up any payload columns or columns that were part of the query from the stores table, because we're not going to revisit the stores table. And then we'll return the resulting row set back to the calling SQL operation. And you'll see that in an execution plan. Notice we see in line ID 3, join filter create, :BF, and then we'll have a table access in-memory full. So for the date dimension table, we're going to scan that table, apply any filter predicates, and create the Bloom filter. We're then going to scan the line order table, again, applying any other filter predicates, and we're going to apply or use the Bloom filter as an additional filter predicate, again, to avoid having to go back and probe the hash table in the PGA. So that's going to give us a significant performance improvement over a traditional hash join, even if the tables were in memory. This also applies to something we call vector group by, part of in-memory aggregation. I will say that I'm just going to touch briefly on this because we're using the same basic process. There is a technical brief dedicated to explaining in-memory aggregation if you're interested, and I'll give you the link to how to get to that technical brief at the end of this presentation. But the bottom line is, rather than using Bloom filters, we're going to use key vectors. That enables us to map to dense grouping keys, because we're going to create an aggregate accumulator in memory. And not only are we going to do the hash join, we're also going to do the aggregation in memory during the scan of the tables. And so that's one of the big benefits of vector group by. And we can not only do the join, but we can do the aggregation or the group by aggregation during the scan of the tables. And then that shows up in the execution plan as a key vector create. Previously, with a standard hash join, we'd see a Bloom filter create. And then we're going to use that key vector as part of our join or scan of the line order table. So same basic mechanism for the hash join. And of course, this leads to the fact that in-memory vector joins will then accelerate or improve the performance of both a regular hash join and a vector group by as well, which is why I'm showing you this. And that leads us into in-memory vector joins. So with in-memory vector joins now, that the optimization is in the matching of the join keys. And now with in-memory vector joins, taking advantage of the in-memory vectorization framework, we're able to use SIMD vector processing to further enhance that join comparison, because now we can do this with multiple values in essentially single instruction, and that can provide a significant improvement in the hash join capabilities, up to 15x in our testing. So that's pretty exciting. It does also leverage join groups, a feature we introduced in 12.2, and then in-memory dynamic scans. So we can actually not only use SIMD vector processing to speed up the join matching, but we can actually parallelize it as well. And so that's what in-memory vector joins is really targeting, that comparison between the join keys. So how do you tell if it was used? Well, similarly to how you can determine whether a join group was used, in a SQL Monitor Active report, for the hash join, there'll be binoculars, and if you click on those binoculars, you'll see additional information in an other information window that'll pop up. And here you see deep vector hash joins is with a value of 1, which means we used an in-memory vector join. And so that's how you can tell whether in-memory vector joins, you took advantage of it for that query. In addition to that, you can control in-memory vector joins with an initialization parameter, in-memory deep vectorization. So if that's set to true, then, and that's the default, then you can take advantage of in-memory vector joins if it meets the right criteria. If you want to disable it, you can set it to false. But obviously, we recommend leaving it set to true, which is why we made it the default. Where can you get more information? So I mentioned the in-memory aggregation technical brief on our resources page. I have listed there all of the technical briefs along with other videos, our Ask Tom office hours session. So there's lots of information about database and memory available on our resources page. And then I've put together some links that cover the main sources of information that you can explore to find out more about database and memory. Thank you.